In the last graph, what we essentially did was fix the location, the latitude, and looked at what happened at each location throughout the course of the year. And that's where we had our familiar sign patterns. In this particular 3D graph that we have here, we're trying to do the opposite. So what I mean by that is we fix the date, and we look at what happens over several different locations. So this graph is much harder to see properly, I think, than the last one, so I'll try to explain it well. The series of black vectors or points that we have close to the axes, these represent what's happening on the day of the first full moon, which is January the 16th. And what we see in this picture is that on the left side of the set of points, the highest one on the left represents a location that is negative 60-degree latitude, so 60 degrees south of the equator. And on the very right side, we see a point that is 60 degrees north of the equator, at 60-degree north latitude. And what you see there is that the amount of sunlight is gradually decreasing as we move from 60 degrees south of the equator and work our way up to 60 degrees north of the equator. The same pattern exists for the blue points, or blue vectors, which is the second full moon of the year, which is February the 14th. We see still that at negative 60 degrees, or 60 degrees south of the equator, the farthest most vector, we have the most sunshine, and at 60 degrees north, we have the least amount. And that, of course, is because it is winter in the northern hemisphere and summer in the southern hemisphere. And the blue lines are kind of a special line because, once again, the blue lines or vectors show us where we have 12 hours of daylight across the globe. So at every location from negative 60 degrees south of the equator to 60 degrees north of the equator in latitude, we have the same amount of sunshine, right about 12 hours, or not sunshine, daytime, and that's about 12 hours. This, of course, represents a date that's really close to the vernal equinox. The date selected was third full moon, which is March 16th, the equinox being March the 20th. We see something really interesting after that equinox. The relationship between the amount of daylight and location gets reversed. So I'm not sure if you can see it well. Maybe in the orange vectors the best, we see that the points that are 60 degrees north of the equator now are getting the most amount of daytime, and the points that are 60 degrees south of the equator are getting the least amount of daytime. I'm going to spin that around now, and maybe a different view will help you see it better, but that was one of my favorite views. So it's kind of tough to look at from that angle. But hopefully when we get back around to the other side, and see it again. Whoa, sorry about that. Yeah, there we see the situation as well. So with the black lines again, we see now here south of the equator is the farthest most point, the highest one dropping down, and that relationship getting reversed after the equinox. As it rotates around, I'll just make a final point, and that point is I didn't continue the data collection process after the fourth full moon just because I thought the graph was already getting pretty jumbled up and hard to understand. But if I would have, when we had reached the autumnal equinox, we would have seen again the reversal of the relationship between the amount of daytime hours for the northern hemisphere and the southern hemisphere. There you hear the bell for a class, so I guess I better run. Thanks.